Until now, we have examined the antennas in microscopic place, microscopic point of view. But this approach doesn't give us the bigger picture. It is the same as a doctor who monitors a cell under microscope. He may know everything about this cell, but will never have a clue what the organ that this cell represents. In fact, does. The same is applicable to antennas. The microscopic point of view does give a hint about the whole thing, but we need to take the bigger picture. And the problem with antennas is very often there is no obvious connection between these two things. So now we will look on antennas as a whole. And let's start with the first. Actually, with the last expression from the previous lecture. If we get the solution of the Helmholtz equation and simplify it to the linear current, linear source, and measure the field around, we'll get to this equation, approximate equation. Antenna engineers love approximate equations. They don't love exact equations for many reasons. Which states that E field here is the source, small section with a current I, in some location on a distance R, and section with size delta L carrying the current I will produce a field E of theta, which will be governed under this equation, where Z0 is the characteristic impedance of this free space, which is Z0 equals 120 times pi or P, or approximately 366 ohms. In a lot of places in electromagnetism or antennas, dimension is ohms, but this is not a resistance, not a conductor property. It's simply a relation between E vector and H vector. And because E vector is volts per meter and H vector is amperes per meter, gives us volts over amperes, which is denoted usually as ohms. But keep in mind, this impedance has nothing to do with current going through conductor. This is 120 pi ohms means that E vector is, let's say, 366 volts per 1 volts per meter per 1 ampere per meter of magnetic field.
What does it mean? The magnetic field has a resistance.
No, it means that when you introduce the electromagnetic wave, E, and connect it to H, it means that E field strength is 366 volts per meter, and magnetic field strength H equals to 1 ampere per meter. It's a field strength of one vector, E vector, to the field strength of the magnetic vector. Nothing more. If you change the medium from free space to, let's say, for instance, Teflon, the relation between these vectors will change. Wave will still propagate, but the ratio between these two vectors will change. And the ratio between these two vectors is called characteristic impedance of the medium.
Yeah, impedance of the medium. Yeah.
But it's not ohms because a current of 1 ampere going through a resistor of 1 ohm and gives 1 volt voltage drop. This is two completely different things.
So this is how much the medium resists for the wave to propagate in it.
It's not resist, but force more one vector or force more the other vector. It's not a resistance. Resistance.
It gives power, additional power to the vector.
Change the ratio between that.
Okay.
Did you grasp that idea?
So, can we describe it with words like attenuation or depolarization?
No attenuation. We're assuming lossless media, like Teflon, for instance, or polyethylene. And one wave from free space goes inside different media, like Teflon. These vectors E and H will rearrange. There won't be 366 volts per meter against 1 ampere per meter. They will change the ratio.
The medium is different.
Yes, because the medium is different.
Yeah.
And the ratio between E and H is called characteristic impedance of the medium.
Okay.
And here we use this for free space. Z0 means free space. ZC is related to some other medium. So if we have a current carrying conductor, short, delta L, carrying a current I, on a distance R, it will produce this field. If we are far enough. That's why this is approximate. If we are not far enough, we'll be in the near field, and we have E R component on this direction and component in direction of propagation. But if we are far enough from the source, we will have only E theta component.
Okay.
And we can divide this to two parts. The first part is a numeric constant, which is Z0 beta, which is 2 pi over lambda. The size of the current amperes, the size of the conductor, phase constant, and the distance. They're all constants here. Complex number, but constant. And the second part depends on the angle of observation. And if you notice this sign of theta, the sign of theta is this, which means the field will be maximum at 90 degrees away from the conductor, and the field will be minimum when aligned with the conductor. And this thing is called antenna radiation pattern.
Why pattern?
Pattern means behavior of performance.
Okay.
In Bulgarian, диаграма на насочено действие. D&D. A variation of radiation with respect of the direction of radiation. Here is what we just have discussed. We have the current with red, and the side. This is called elementary dipole, very short dipole. And we have radiation in each direction, but the size of the radiated signal varies with the angular coordinate. And because the source has a symmetry in one plane, the overall pattern, which is three-dimensional figure, is also symmetrical in one plane. So it looks like a donut. Okay. So this is how the very simple radiation pattern looks like. And now, what type of patterns we do have? Generally, three types. The first type is idealistic, so-called isotropic pattern. Isotropic means in each direction of radiation we have the same value of radiation. Which source has isotropic pattern?
First.
Yes, but in
Spherical.
the nature, what is
Something that's symmetrical.
who radiates constant power in each direction?
The sun.
The sun, of course. The sun has isotropic pattern, almost isotropic. In practice, there are very few isotropic sources, but it is used as a reference to compare one antenna to another. We cannot do that directly. We compare it to a isotropic source and then say this one radiates more directive than something else.
The only way of sending signals. This is just a 3D image of what we saw on the video. I assume because we saw waves spread in a similar pattern, just in 2D.
Yes. Yes. This is because we're three-dimensional creatures and hardly perceive three-dimensional processes. Because we are 3D creatures, we very hardly interpret 3D processes. We easily understand two-dimensional processes. For the same reason, four-dimensional creature, we are very simple for him. You know, if you have watched Interstellar,
Yeah. 7 inch.
yes. The second type, directive antennas. Directive pattern. Pattern, when we have one predominant direction of radiation, and the other are either suppressed, either minimal. This is most of the cases. Antennas are designed for this type of. Why so? Because the point of interest is in a specific location. For instance, if we are satellite, all our customers are on the Earth, and the satellite must transmit directly to one continent or sometimes one country. And in case of large countries, sometimes in one region, let's say big city, like Dallas, Los Angeles, they need a very focused pattern. And point-to-point links also. And the third type is omni-antenna, when we have one non-directional pattern in one plane and directional in other plane. Can you give me an example of occasion when we need omnidirectional coverage?
Radio.
Radio, exactly. All the customers are located in one plane. They live in a city. The city is 20 kilometers, but by 10 meters height. So basically, all the customers are in one plane. We don't have customers flying above. So we need omnidirectional pattern of the radio station. And having an antenna, we cut this pattern into sections, cross sections. And the natural way of cutting is horizontal and vertical, which is natural for us. Everything which is on a sea level is horizontal, and everything on orthogonal plane is vertical. The problem happens when we go to the space and there is no up and down. But we still have to make difference which antenna how radiates. And then we form a concept of E-plane and H-plane. And one antenna radiates the E field, this is the E-plane, and oppositely, the other plane is H-plane. And that's how, if we have this antenna placed on a spacecraft, we can tell orientation of the antenna to orientation of the pattern. So it's very easy when we are on the ground. We can see the things here, and there is a gravity, but if we go to the moon, things change. And I can give you an example. Here is our observation point, and here is the moon. We have colleagues, astronomers, and they have seen the moon very carefully. They can confirm the moon is round. And if we get here on top of the moon and put our antenna and transmit toward the Earth, it will transmit on what polarization? Vertical, all right?
Yeah.
Vertical, good. We see it. But then the moonwalker decide to go around and start to transmit from here. And for him, polarization is still vertical. And he asks him, what polarization are you transmitting? I'm transmitting on vertical. But you receive nothing because...
It's horizontal.
Exactly. And this happens all the time. And what?
Maybe with the moon is not a good example because it's always facing with the same side.
It's easy to know what is what, yes. But if we fly a spacecraft, on each circle it transmits in different polarization.
Yeah.
So we have to run the numbers every time and align the antenna polarization with the polarization of the source. Very good. And now, as we love 2D things, represent the same pattern in this manner. For human creatures, human beings, the natural coordinate system is polar coordinates. The problem is, the beautiful thing of this is that we put ourselves here and watch toward the maximum, and now this antenna radiates maximum here, less, and here from our shoulders aside, nothing. So this is easy to interpret, perceive. It's more natural for us. But then, in this location here, our instruments detect something that we don't obviously see. And start to ask ourselves, why we do detect something that we don't see? And then we decide to switch to logarithmic scale. And the logarithmic scale makes the small things to spike out. And we see that in logarithmic scale, on a level minus 40 decibels, actually there is things that radiate emissions, but since they are 10,000 times less than the main radiation, main emission, they are not noticeable in a linear scale, but most of the equipment works with logarithmic amplifiers or small signals. So these small radiations are quite noticeable with instrumentation. And that's why are introducing the logarithmic scale in representing the antenna pattern. And then we go even further, because here we need a protractor or something angle measuring instrument to make any calculation. For instance, if the manufacturer of the antenna delivers us the pattern resistor, I'm clear what this antenna is doing, but if you want to take any number, it's not so easy. And that's why this Cartesian logarithmic scale is the most used way to represent antenna pattern. That's how they are specified. So you can easily grab a ruler and measure the values. You see the small numbers clearly and make any necessary measurements, etc. Logarithmic Cartesian. Yes, please.
Is it pretty much the same when we talk about different types of waves, like pressure waves? For example, the transmitter and the receiver would be a speaker and a microphone.
Absolutely, yes.
Because these arrays and these patterns look a lot like when you're designing a collaboration space, like a conference room, for example. What type of microphone you should put in on a conference table, one that has a full array, because everybody is going to be speaking like this, with respect to one that you would have on a headset, where you would want it to be very close range, so you don't hear any of the external.
One-to-one applicable to microphones. They also have radiation, in their case, pattern of reception. So if you use it for radio show, you need one type of microphone. If you want to record bird songs, you use highly directive microphone. If you want to record auditory, third type of microphone or microphone array also. Like antenna array, there is arrays of microphones that they can very selectively pick the source or change the direction of reception. Waves are similar, although no, acoustic waves are longitudinal material waves, and electromagnetic waves are transverse. Yes, the way they propagate is identical, and the sources and receptors.
And why we have smaller emissions?
This is how antenna works.
But what causes them physically?
We just explained them in the past. I'm just kidding. You will see. You will see why exactly. On microscopic level, it's not possible to understand. You need to. You will see.
Okay.
And this is actually
This.
how one directive antenna works and radiates. This is the components of the antenna radiation pattern.
In what radiation zone are these small emissions that we can classify? The small emissions near the antenna itself.
Yes, they're called side lobes.
The side lobes. Yeah, but, in what reactive zone are they?
Everything you see is in the far field. In the near field, there is no pattern like that.
Okay.
Pattern is only formed once the wave make enough of interferences, enough of if you have a source that radiates and the adjacent point also radiates and the adjacent point also radiates, and this radiations from each point they zoom, and this goes interference pattern, and you need a lot of interference patterns to sum until they form the radiation pattern. If you're too close to the sources, you won't see this thing. You can see it only far away from the source.
And what is close to the source?
2D squared over lambda is far enough to see a formed stable pattern.
This is still in the logarithmic scheme.
This is, yes, logarithmic scheme. And what are the main components? First of all is this large thing in the middle, where the most of the energy is concentrated. It is called main lobe. Main lobe. Na български главен лист. These radiations from a side are called side lobes. На български странични листа. И това, което е this which is directed backward is called back lobes. And what you can see, there is a drops between the lobes.
Minimum.
Yes, these minimums are called pattern nulls.
Nodes.
Null, zeros,
Nodes.
nulls.
Okay.
So if you happen to be in this point, when the null is directed, you will see no radiation. Even here. Here you see something, here you see something, here I'm gonna see anything. Yes.
But this is.
Yes.
But this travel through space. The
Yes.
energy this way.
Yes.
So when I pass the nose, I will get signal.
Yes.
Okay.
And here is the measures related to the beam. So we plot the antenna pattern based on field strength F theta T.
Mm-hmm.
And if the maximum is normalized to 1, on position 0.7, we measure the the antenna pattern beam width. So this, let's say 20 degrees, we say the beam width of antenna is 20 degrees. Which antenna is more directive? 20 degrees antenna or 10 degrees antenna? 10, yes, because the pattern is narrower. And here, if we square the pattern and plot it into power measures, so field squared gives power, this will be the same angle but measure it on the level 0.5. And that's why in the English literature this is called half power beam width. And in each antenna catalog, this is the number that we get. Half power beam width. And of course in decibels, it will be minus 3 dBs down from the pattern peak. Half power beam width. And similarly, the angular distance between the first nose, how is it called? First null beam width. Combination of first and the second will give us a clue about the shape of the main beam. It was invented in the times where there were no computers and you have rely only on your logarithmic ruler and power tables to calculate something.
Yeah.
So these numbers were very important. Now it's easy. You click and pattern is plotted. Oh, this is this, this is that. The computer will do this for me. There was times not so long ago when to get a single pattern you have to work a week or so. Which is now, you will see clicker. And that's how things look like. Main beam, half power beam width, from here to here, first lobe beam width, side lobes, and here on the back is the back lobe. What does it mean back lobe? It means that even until it's pointing this way, something is going to be transmitted in a reverse direction. Good. Do you have any questions so far?
This is a normal conducting wire, for example, used for antenna. What shape of antenna produces this pattern?
Parabolic antenna. Simple conductor produces much broader. And we will simulate it tomorrow. Very good question, actually. So it relates the practice with everything clear so far. It's easy, no.
Maybe the last slide I didn't understand the last picture in decibels. What's the point of it and why does it look like this?
This one?
Yes.
Yeah.
It's because decibels highlight the small numbers. That's why this side low on minus 20 decibels, minus 15, looks like this one on 0. But in fact, the power is much less here than. But because we work easy with decibels in the radio science, it's easy to say this is minus 30 decibels and this is minus 60 decibels, and in fact it will be 1,000 and 1,000,000th fraction of a unit.
Is this because this unit of decibels is somehow connected to surface area?
No, it's because of the human apparatus of hearing. We hear.
Hearing, vision, and the numbers are smaller. So if you have 50 decibels and have to divide it by 2, you have 47 decibels. 3 decibels difference is 2 times. This is much easier to understand than having 10,000 times, 100,000 times, which is 50 decibels, and 50,000 times, which is half of it. With decibels, we add and subtract easy, and with linear numbers, we have to make division and multiplication, which is more complicated. Decibels are it's another form of simplification, like the complex number, another type to make our life easier. Nothing more. And then let's go to the next concept, which is called radiation intensity. And first thing that I love to ask my students, I asking this all the time, each year, what is radian? And how it is delivered to us.
First, it's a measure used for measuring angles.
Yes.
And it's actually more natural because it stems from the circumference of a circle of pi. How many times we can map
Yes, that's the
radius of the circle.
Exactly.
on it.
In the ancient Egypt, people has very few measuring things like pole and a rope. And the easiest way to create the circle is to put the pole here, extend the rope, and then start to walk. And this will form a circle, right?
Yeah.
And then what we gonna do? We get this rope. What is the length of the rope? Radius, of course. And then put it over this circle. and then draw the other radius. And what is the angle between these two radii?
60 degrees.
Uh-uh.
What radian?
Pi over 3 radians.
Uh-uh.
Yeah.
It's amazing that ancient Egyptians knew more than us, right?
How many times did we?
One. We get the radius here and put it here.
This is one.
This is
Yes,
one
It's the length of
Pi.
the arc. Of
one radian. The length of the arc is the same as the angle.
Oh, okay.
And how many times we can do this?
6 times.
628.
Times pi.
That's how Egyptians invented the radian. Everything else, like this 360, comes from where?
The number of days in
2 times pi is approximately 6, so 6 times.
In which science? Maybe philosophy. In engineering is
I don't
6.28. I'm just kidding. Pi is concept that comes eventually. The original angle was this. Radius, Latin word for this, and something that radiates. The length of the rope and the adjacent radius. That's how they build pyramids, you know. They use things like that. And eventually, Greeks stole everything and say, I'm Pythagoras and invented the Pythagoras theorem. I'm Thales from Milet and invented the similar triangles. Well, it was delivered from Egypt. And this is proven fact. Okay. And why is this related to antennas? Because if we do the same but with a 3D figure like a sphere, and then we plot curved area, which has an area r squared. You know, it will be a circle, but like a hat that some people wear. Like this. The area is r squared. And we'll look toward the edges. What we will see? Cone. Exactly. And what will be the merit of this cone? The measure.
Spherical angle.
Spherical angle of size 1
radian.
Steradian.
steradian. It's a merit of space angle, 3D angle. So the merit of 2D angle is radian, and the merit of 3D angle is steradian. This cone is the merit of angle, like the sector. And why this is important? It is important because if we put a source here in the center and it starts to radiate, part of this radiation will be enclosed into this funnel, in this cone. And we have exact way to measure how much power is going within a unity of space angle. And the measure of this thing is called radiation intensity. Do you grasp the concept? What will happen if we expand the sphere?
It will become bigger. It will become bigger.
Yes.
The range.
Yes. Will radiation intensity change?
It will decrease.
Because it's per square. it's per
This is the
area.
trick, guys. What will change and what will not change?
The area will change.
Exactly.